Go with my favorite game. Yankees away this week. How it shows.
All right, excellent.
Thank you.
Okay, great. So we have Jeff Edmonds visiting us from York, telling us about gradient descent.
Excellent. And I'm a FACE student. All right, so I'm not a machine learning person, so this is clearly not to a machine learning group. It's I wanted to learn some of it, and I've made a lot of. I'm sort of a PowerPoint slide addict, so I've made lots of talks on machine learning. If anybody wants to look at them, I think I like them. And I read this one paper, this one here, that surprised me. I thought there wasn't a lot of known. So Jeff Hinton and them say if you throw a lot of data at things and a lot of parameters, everything's great. And I often talk to John, who was here and is now with me, that says, yeah, but what do we understand about it? And so this is a paper that talks about things that we understand. So the general topic, oh, by the way, I did this same talk yesterday and people had 2 hours of hard questions. So feel free to do that as well. So this is your standard neural net. We get training data, input output pairs, our goal, and the paper is about overfitting. So having lots of parameters. We have so many, the number of parameters is the weights on the edges, and we have way more than the amount of training data, right? So polynomial times more. And so then the question, is this paper interesting? Because if the number of parameters is just equal to the training data, then a depth-2 circuit can just do table lookup, right? And then you have the problem, well, if it overfits so well, does it generalize? So I have read a couple papers on generalizing, and not that much is known, but at the end I have some thoughts about that. So so what are we doing? We're asking, yeah, but the question is gradient descent. How well does it do, right? Does it converge quickly? Does it get stuck in a local minimum, right? One of the things that always surprises me as I learn things about machine learning is how much of it was taught to me here as a graduate student, right? It's surprising how little actual new things are known, right? So what does this paper say? It proves that if you over-parameterize, then it proves with high probability you'll get the perfect answer on all your training data. I only put epsilon because if they're real numbers, you can only get so close. And it does it in time polynomial in the number of training data, right? So don't think this is polynomial in the number of inputs to your function, right? We have a lot more training data than that, right? But so this surprised me, right? And I asked various people, and I didn't meet anybody who knew this. So I thought we should do it. The other thing I think that is interesting about it is that the weights that it finds are completely random plus a small change, right? And so what that says to me is if you're hoping to do, a whole field is, can you explain your machine to us? And this says, no, the machine that we're getting is completely random. There's no way you're going to understand it.
This is just a convergence to the training data.
Just the training data.
Nothing about the generalization.
We're not, yeah, nothing about generalization. But at the very end of the talk, if we don't run out of time, I have a few things that are known about that, which is very little. So in practice, right, it goes back to Jeff Hinton will say in practice, it does generalize pretty well, right? But there's limited theory about it.
Could I have some questions about the model? Are you going to say something or?
But you say whatever. We're going to definitely yes. Ask,
okay.
Yeah.
Are you going to define?
Yeah.
Oh, okay, great. Oh, then fine.
This is just the
yeah,
high level here.
It just converges with arbitrary gradient descent or by back propagation. It has to actually do a certain type of,
Just you go in the direction of steepest descent.
for the whole kind of thing without worrying about the layered, network.
Yeah. All right, so model. The paper claims to prove this theorem for just about any setting you can imagine. And there's been various versions of the paper, and this version looks at real numbers. So we're doing regression. And the error function is your standard one. So the notation here, the purple X's are our training data input. And then we have a number of outputs, and the red is the output of the machine. And then the training data gives you the supervisor's answer, and you take the difference of them and square and sum up overall training data. And here they give you a number of different outputs, so we just do all of those, right? And then this paper is doing rectilinear, nonlinear thing. Why? Because it's the harder one. Previous papers did sigmoids. It's all the same, right? And as I said, it plans to do it for lots of models. Also, let me give you a little warning. The paper, this version of the paper, and there's lots of versions, is 53 pages of very hard math, and I'm going to throw lots under the bus for this talk. And so when they had a lot of questions, they were saying, "Oh, what about this thing that you threw under the bus?" And we can do this. And all right, so gradient descent. You don't have to read all this. You probably all know we have the space of our weights, and we change the weights in the direction that decrease the error in the steepest descent method, right? So what did we talk about when I was a graduate student here, right? We said the worst case is that there are lots and lots of local minimums, lots of them, and one of them is particularly low. And so you're going to have to spend exponential time finding it, right? That's what everybody was worried about. What's the best case? Well, the best case scenario is it's convex, but we're not going to get that, right? So what is another scenario is that there are lots of local minimum, but they're all perfect, right? And this is the scenario, right? So what the algorithm is, you start in a random place, you do a little bit of time, and you find an optimal solution, right? And so of course, when I first read the abstract, I thought, how can you ever prove that this is the global optimum, right? Because you can't look over this whole space. But if it's perfect, right? You can't argue about that, right? And so what the main idea here is that we stay within a very small ball of this random setting. So everything is going to look random, and we're just staying within this little ball, all right? So that's this paper that over-parameterizes and gets what we want.
And this is conceivable just because, not just because, it's conceivable because there are enough parameters to incorporate the whole data inside your network.
Oh, well, yeah, you certainly need to have as many parameters is the amount of training data, right? That's for sure.
Yeah.
And then on top of it, we have way. When they say over,
Yeah.
they mean over,
Right.
right? But polynomial,
Okay.
but more, yeah.
Okay, and when you say the number of parameters more than the training data, you mean we're counting the number of data points, or we're also counting the number of coordinates within each data point? So,
No, it's the number of XY pairs.
okay.
Yeah. But these numbers are also big that if we multiplied by that, it wouldn't matter.
Okay, great. Okay.
Right.
Yeah, okay.
That would just change the polynomial a little bit.
Yeah.
All right, so what's the algorithm? As I said already, you start in a random place, and you only run a little bit of time. So we're within this ball. So where are we? Here's the random weights. We add some change to it that's very small, and we're within this ball, right? And
Why is that different than just the random thing? Sorry. You're perturbing this random thing by a little bit.
No, sorry. The algorithm is you start in a random place and you do random and you do gradient descent. But you don't run gradient descent for very long.
Okay.
And hence you haven't moved very far. You prove that you haven't moved very far.
Okay.
And hence you're somewhere within a ball.
The weights
Right?
are in the ball. Okay.
Right?
Okay.
And now I would say 90% of the questions that were asked yesterday were about the fact of do you have independence between your variables, right? And the thing that I kept saying is for the most of this talk, we're going to be proving things about what random weights do, right? And then at the very end, we'll wave our hands slightly and say, well, during the gradient descent, we moved a little bit, but we don't know where we moved, right? We don't understand what that's doing. So we're going to assume that an adversary tells you where you are within that ball, right? So all the confusion about where we're going is hidden under the fact that an adversary is doing worst case, right? And then we say, well, we understand random weights, and if you just move a little bit from random weights, you don't have to do anything real. It's just vector algebra saying, well, things haven't changed much, right? So we'll have, at the end, we'll have one page that says, hand wave, 10 pages of mathematics. We didn't move very far, and so things didn't change by very much, right? But the focus today will be on looking at random weights, where everything is random and independent. So everything is nice. Yeah.
So it's basically after a small amount of time, the weights are here. Are you going to continue running the algorithm, or the algorithm has ended and you found the local minimum?
It's found it. So here's the magic. You give an amount of time and a step size so that two things happen. One, within this time, you find the optimal solution. And two, you haven't moved so far that you can't still say it looked random, right? So it's pretty nice, right?
I'm not quite sure where is the adversary picking the starting point, or is
No.
that random?
No, he's telling you where in the ball you are.
Okay, but the problem, but you're doing gradient descent, so that's a deterministic algorithm, right? So,
Yeah.
So once you pick the starting point, where you go is
Deterministic, but we don't understand it.
right.
All right? So all we can prove about the gradient descent is that it finds the optimal solution and it doesn't move very far. Right? Now, so because it doesn't move very far, you're within the ball. And then we can say, well, I don't know really where you are in the ball, but it doesn't matter, because wherever you're in the ball, the machine doesn't change. What property do we want of the machine is that when it takes a gradient descent step, the error comes down by a lot. That's the property that we care about. So the main thing we're going to do today is prove that for random weights, the error comes down exponentially.
So what you do is pick a random weight, then the adversary gets to perturb that.
Yeah.
But then you perform perform gradient descent, so that's where the,
Well, during the algorithm will do gradient descent starting at the random spot, but that's just the first step, right? So yesterday people kept saying, yeah, but that's just the first step. Yeah, but for multiple steps, after we've done it for a while, now we're somewhere within the ball. And how can I say what it's going to do within the ball? I still want it to behave well. Well, the claim is that if you're close enough to random, everything we say about random will still apply. And so the second step of gradient descent will be good. And the third step of gradient descent will be good.
So
Right?
we're modeling the 10th step of gradient descent as an adversarial point, which is, but there are many random-like properties.
Yes,
Yeah.
exactly. So what we're going to prove is that, yeah, you take a random setting, you perturb it by a small amount chosen by the adversary because we don't know where gradient descent's going, and it will still have the property that a step of gradient descent will bring the error down exponentially.
I guess I lost something about the beginning. Are we assuming that there are lots of good local minima? That's the assumption.
No, that's the magic.
That's the magic. So even though there might be just one good local minima,
No, this is proving
that there are many.
there are an exponential number of them.
Or when you have enough over.
When you have, yeah, if you increase the parameters, then your space is really big, and at worst, it's
Okay.
multiplying the
Oh, I
little
see.
things.
I see, but you have to be suitably over.
Yes, yes,
Is there-
right. In fact, why do we need to over-parameterize? So that a random location has this property.
And this will fit any point, any day.
Any data,
So this is a very dense set
Yeah.
of functions in some way.
yeah.
This is very surprising.
Yeah, that's what I said. That's,
And it should say something, maybe just even plain local search, combinatorial local search algorithms, but let's go ahead.
so what if the adversary always chooses W prime to be 0, then nothing's happening.
oh, but that's not the problem. When we use the adversary, it's just so that we say the next step will be a good gradient descent step, right? So there's two separate things. One, proving that as long as you're in the ball, gradient descent steps do make lots of progress. And then another thing, as long as you make enough progress, you'll find the optimal solution, right? This part doesn't use the adversary.
I see.
This part says we're getting there. This part says we don't need to worry about all the non-independence, right? At the random spot, we have great independence. You take one step, and now we can no longer say what this machine is doing, right? And this throws all that under the bus. Right?
But you're letting the adversary choose what happens in that part.
But not very far,
Yeah, but if it doesn't go anywhere, then you're back to where you started from.
which is good because where we start works really well.
Then you've made no progress.
No, but you're now over on this side, which says as long as we keep making progress, we'll get the solution. This side says no matter where you are, you'll make progress. This side, it says if you make progress, you'll get there,
Okay.
right?
Is there any worry about the gradients being too large so that the steps are too big?
Yes. So in this, what we have to prove is that what does it mean to be good? Is the gradients are big enough that you make progress and not too big so you fall out of your ball, right? So both need to be proved.
Yet within that ball, there is some other function that, there is another setting of parameters that would approximate
Any other thing, right?
and it does it without having high gradient, which, yeah, okay.
Yeah, in fact,
Yeah.
my brain kept saying, when thinking about generalizing, if your set of models is small, then it should generalize. And I'm like, this is very small, right? But in terms of VC dimension, it computes everything, right? So it has full VC dimension, this little ball, right? So we can't expect it to generalize well. Right? All right, so this just says all our weights are going to be random and independent, so we can prove things about them. And this says what we keep talking about. If you shift by just a small amount, then things don't change by much, right? And so what do we want? What do we mean by things work well? We mean that you start in a random place, and each step decreases the error by a multiplicative constant amount, right? So that we all know then it just in log of the error steps times this factor, it gets there, right? All right, so now let's do steepest descent. We take the derivatives in all direction. We change our weights by some step size times that derivative. And so this is just writing it down for one weight, because I'll often be focusing on one weight, right? You take the change in one weight is the derivative of the error with respect to that weight times the step size, right?
And do we have to choose the step value as a function of something?
Very carefully. Well, yes, we'll do that in about 2 slides from now. All right, so now we know the error here, we need to calculate the error here. And of course, the first step is you do a linear approximation, right? So you shift by a small amount, and so you have the old error plus the derivative times the step size, right? But that's clearly not necessarily good enough because it's curved. And so you have to add on the second order Taylor guy, right? And then this is, as I said, the new paper is dealing with rectilinear, and right when you're right in here, things aren't pretty, right? So there's another whole bunch of scary math that we're going to not talk about, where there are terms that deal with that, right? And the whole point, as you can imagine, is that if your change is small enough, then these terms go away, right? And so that is why we make the step size really small, right? So that this stuff goes away. And you'll see the step size is 1 over the number of training data to the 5. So that's a big number, right? A small number. And that's why the running time is big, right? The running time is not big because of the log of the error. That's a non-issue. The running time is big because the step size is small, right? And then just as an aside, they have one sentence that says, in the previous papers, you didn't need this, right? Because this is well behaved.
There were previous papers before?
Oh, yeah, you don't come up with a 53-page paper.
So people had proved this result for sigmoid before?
Yes, yeah. And this paper is a decade old. I don't know when they first did this stuff.
Published and well accepted and everything?
As far as I know.
Okay.
It's published, definitely published. And somebody in Vietnam, I said, I want to know the theory, and they handed me this paper. All right, so we're going to just stick with the linear because we got rid of all those terms by making our step size small.
And anyway, this ReLU function seems to have, it is piecewise linear.
Yeah. The problem is just this versus this,
Yeah.
right? Yes, I mean, this is derivative 0 and this derivative 1, right? So those clearly aren't a problem. And in fact, I can tell you the punchline at why if you change things, it doesn't matter, is because when you change the weights just slightly, very few of your rectilinears jump from here to here. And then if you ignore those, it's all linear. And so it's just easy, right? All right, so here we just changing the step sizes of this, which kind of I never realized it's kind of cool. It brings a square here. And now this math here is just for one weight, one training data, one weight, right? So you have to sort of say, well, we need to deal with each of the weights, and you have to do with each of the training data. And I'm lying a little bit where this versus this. Why is this sum on the inside? But these ones are independent, right? Their weights changing, different weights. Well, these ones, one training data could make my weight change this way, and another training data could make my weight come back, right? So they cancel out in there, and that becomes a problem, right? So what do we have to prove? We have to prove that this change in error is proportional to the error, right? And when I mean constant here, of course that constant has lots of m's in it and stuff, right? It's right, and so that we get what we're claiming, right? And then as was said over there, you can't leave the ball, and so this is saying the error doesn't change much, but really what we need is that the weights don't change much, right? So you need that too. And proving for a fixed, what we're going to do mostly is going to work for a fixed input, right? And that's proving this derivative is surprisingly easy. Then the hard part is we have to sum up for all x's. And when we're doing an upper bound, you just multiply by the number of x's. But for the lower bound, the scary thing is that these could all cancel, right? And so we have to bring in something else that I didn't tell you about before. Remember, we have our training data, our x's and our y's that we're trying to learn. Well, what happens if I have two x's that are the same and they have different y's? Well, you clearly can't learn that, right? So you got to fix that problem. And the way we fix it is by saying the minimal distance between two any x's has to be a certain bigness, right? Certain amount. And then we're certainly not going to cover this, but and this is actually making this smaller. So we'll say one training data does really well. The others might take away from that, but they won't take away all of it, right? So everybody good with it? More or less? So now we're going to focus on just random weights. So don't talk about independence, except we just got purely random weights. We got one training data where we're looking at what is the sum of these derivatives squared compared to the error, right? All right, so here's our machine again. We start with random weights again. We say that they're all random. And so let's first say that we take our training data and we normalize it. It's a vector. We normalize it so it's length 1, Euclidean 1. And the first thing we want is we don't want things to blow up, right? We want everything to be well behaved. So for each layer, if you look at the vector of values, the length will stay at 1, right? And this in some ways is just kind of obvious, because if you play with, so here I'm saying that the weights are normal with expectation 0 and this very small variance, right? So they're really little things. And you set this right, and you'll get this property, right? So it's not too surprising, but it was fun for me to play with this anyway. So I'm going to do it by induction, one layer at a time. And I will say the paper says, well, that's not hard to do, but you have to be fancier or else the error blows up with depth. And we're going to just throw that under the bus too and worry about one step. All right, so I'm actually going to hand wave this proof 3 times because I saw it 3 different ways and I thought each of them added something. All right, so the first way is just what are these values? So the purple value is the output of this neuron, right? So it's post the nonlinear bit. And the blue is before the nonlinear bit, right? So the blue is the sum over all these values times their weights, right? And because the weights have this distribution, each one is plus or minus 1 over the square root of m. And because of this, these are more or less plus or minus the same. And since we want to do the same, this is more or less the same. And then you add up over m, and the math doesn't work, right? So the reason I'm doing this example is to show why the math works. It's basically these plus or minuses are random, so the cancellation is a random walk, right? And the random walk gives you a deviation of square root of m, and you bring in square root of m, and it works, right? And I thought I knew all about variances, but this helped me understand it better, actually. So these weights are normal, and then you multiply it by what is now a constant, and it brings the constant squared, right? And then here's the magic step, which I know you all know, but there's so much magic happening here, right? If you look at the sum of a bunch of normals, then the variance adds, right? Which is where the square root in the random walk comes from, right? So this requires them to be independent, right? So you take the sum of a bunch of independent normal random well, any random variables, and their variances add, right? And so then when you take the square root of the variance is why you get random walks of length square root of n, right? So you can see there's a lot hidden in this line, right? Everybody kind of following that?
So the y's are the y's are the sums of the appropriate x's,
The y's is the output of this layer.
which is the sum of all the x's plugged into ReLU, or this ReLU function.
Yeah, we're not worrying about where it came from at the moment. We're just doing one level. So you get the output, you get the input of this layer,
Yeah.
and then the output of this layer is this linear sum, right?
And you're making the assumption that the y's are infinite, even though they're all functions of the same axis.
No, we're not assuming here I'm assuming the y's are constants because we did that level already. And now we look at new randomness of the lever of the weights. And these weights are definitely independent because they're different weights, right?
So the question, I think, is it the same as we have a fixed vector y, we're multiplying
Yes.
it by a
Random weight.
a
Yes.
random matrix
Yes.
full of Gaussians and zeros.
Yes,
All the Gaussians are independent.
yes,
And the question is what happens to the
Yes.
weight of the output. Okay,
Yes.
so
Where does the nonlinear thing come in then?
but we haven't gotten to it yet. It goes from blue to purple at the next layer. We're going to do it right now
So that's what these ZJs are, and we're going to plug it into the
to get y's,
Yes.
right? The blue Z's
Yeah.
are pre,
Yeah.
and the Z's are the purple are post, right? All right, so here we have a sum of squares, which we know is 1, right? And then that just gives us, right? This is the variance, so this is the expectation of the square, and so we know the expectation of the square is 2 over m, and now we're doing our nonlinear thing. And there's a bit of a hand wavy here, but the sign of z, you agree, is completely random, right? So you zero it with probability 1/2, right? And so the expected value just comes down by a factor of 2. Right? So there's lots of magic going in here. We can all sigh, but at this point, what are the blues? The blues are values whose sign is negative. Sign is is random,
Yeah.
right? 50-50 random. So the square here, when these things are positive, they don't change anything. And when these things are negative, you kill it off. So you kill off half of them.
They are,
Right.
they are dependent, but that's irrelevant for the expectation.
Yeah, yeah. And they're not really, because we could have first done the randomness except for the sign and then added on the randomness of the sign, right?
Actually, oh yeah, fine, I see. When no edge is used in two different computations. No green edge is used in two different computations. So they are truly independent.
Yeah.
Yeah, okay.
Yeah. All right, and so then we can add it all up, right? And we get 1. Yeah.
So the Ys you have on this slide are different than the Ys you had on the previous slide.
Yeah, the Ys here are the outputs of this level. The Ys here are the outputs of that level.
Let's see.
Yeah, yeah. It's a toss-up. You put in lots of indexes, and that can either help you or hurt you, right? In the understanding. So yeah, that's the picture. Tells you the values, right? Everybody get that? And as I said, then that's true plus or minus some epsilon. And if we did it by induction, the epsilon would be growing exponentially with the depth. And the paper works hard to have that not happen. And that's reasonable too, because the different layers are independent, right? Some will be plus epsilon and some will be minus epsilons, and they're going to cancel out, right? You probably get a square root of L in there instead of a. Anyway, all right, so now we're going to start taking derivatives. But before that, here's some pre-activation value at that level, and we're going to feed it all the way over to the one of the outputs, and we're gonna ask, if you change this a little bit, how much does that change? And that's a derivative, but intuitively I find it's nice to talk about it being a super edge across here, and that's the weight of the super edge. So if you change this, then the derivative is the weight of the super edge, right? And you can think about it as derivatives or weights, as you see so. So we want to calculate what the super edge weight is. And when I said I was going to do that last proof 3 times, this is kind of a third way of thinking about it. All right? So what is this super weight? Well, it's the sum over all paths from here to here of the product of the weights along the path, right? Assuming that none of the rectilinears kill it. Right? If any rectilinear along the way zeroes it, then it's gone. But assuming it doesn't die, it's going to be the sum of these weights. Right? And different paths are going to have different share edges. So that's why I put independence in brackets. But if everything is independent, then the variance of this, right, is just going to be the sum of the paths and the sum of the product. Right? Kind of like what we did before. And then the variance of each edge, where it was 1 over m, and we multiplied the length of the path, right? So we get that. And then each edge has a probability of being zeroed, right? So that got rid of all the 2's. And then how many paths do we have? Well, it's the length minus 1 because here's the length 2 and here we're only multiplying by m, right? So there's the minus 1 there. And it all works out to be what we kind of got before. Basically says what many paths, long paths do is basically the same as what one path does, right? All right, so now that just says what we did before. So now we want to take our derivative, right? So let this be the output of a previous layer. And we have all those weights. And so what's the z? This is what we had before. These z's are the linear combination of those. And then what's our output? Now here we can either be talking about chain rule of derivatives, but keeping it in the same weight form, right? The output y is the sum over all these various z's multiplied by our weight, our superweight, right? So that gives us this double sum. We're summing over these and summing over these, right? Which is nice because now we choose a particular one, a particular weight, right? And we differentiate with respect to this weight. We go into, is the speed good? Should I go slower or faster? Are you guys good? Right.
Is the ZJ,
Which?
yeah, is the ZJ in the double sum? Second one. ZJ is.
You're absolutely right. That should be no. The one is summing here and the one is summing here, and R is fixed.
Yeah, like, okay. Just from like the shape of like the equation, I was expecting it to be before that second W term, the ZJ.
Well, they're all linear. This is a sum of these ones, and this is a sum of these ones.
Right.
So it's just a sum of a sum.
Yeah, you're expanding it, okay.
Yeah. And we're going to take the derivative now. So all of these, I made them into to primes.
Yeah.
Why? Because we're choosing particular ones, which we're going to differentiate with respect to. And everything goes away. I mean, we're differentiating with respect to this, so it goes away, right? And we simply get, right, this value times this value.
Yeah, well, I'm not going to follow the details at
Yeah.
this point, but going back to your other point, you said all this kind of intuitively tells us it doesn't generalize. I think you said, but yet in practice it does generalize.
Yeah.
So where's the disconnect? How does this? How do we square this?
I have a few slides about that at the end, and really, I would say nobody really knows. And the other thing is there's some thinking that if you take a machine and you take what its derivative, I mean, it's kind of this here. You make a small change here, how much change happens there, right? If that's small, then, right? So if I'm trying to fit this data and my machine is doing this,
Yeah.
then it's not going to generalize well, right? So it generalizes well when the machine has small derivative. And so we'll also, so this right here then says, right here it says the derivative of these is small, right? All these derivatives are small. So that says, well, it doesn't do this. It does something more smooth. And so maybe it generalizes well. Right? And really, that's all we got. I'm sorry.
Maybe they don't over-parameterize it so much in real life.
Yeah, I mean, we're gonna. So we're at the. There's another paper that I was sent just 2 days ago, and it says that if you want your derivatives of your machine to be small, you need some over-parameterization. The number m has to be the amount of data times the dimension. So as soon as you get more than the number of data, then you're starting to overfit. And this says if you want your machine to be smooth, then you really do need some over-parameterization, right? So I think the bottom line is you're not going to fit well unless the number of parameters is more than the number of data. And then you're not going to get packed learning, right? Packed learning is just gone. Packed learning requires that the number of parameters be less than the training data, right? So right there's a disconnect, right? If you want packed learning, you need few parameters. If you want to actually learn, you need a lot of parameters, right? So what are we left with? Well, and also, one thing that really, anytime I try to think, can I prove a theorem here, where you always have to go back to, if what you're learning is random data, random y's, if your y's are random, then you cannot learn that data without at least the number of parameters being the number of data things, right? And you're never going to generalize, right? Because you're never going to predict those y's, right? Just so if you want a general theorem, it's not happening, right? You need to say something about the function you're computing, right? And what can you say? Well, you can say it can be computed by a small circuit, which is really saying it can be computed by a small neural net, right? So that's pretty hard.
But the pack learning people all the time look at special, talk about what functions are learnable and not learnable, right?
Yeah, and I don't have a claim to have a complete understanding of it, but I asked people for those questions and were sent a few papers, and all the papers I sent, I think gives to be lame.
Lame.
Yeah. So the one thing says that if the function that you're trying to fit has small derivative, then what? Then what? Well, here's another funny thing is that what is M? Is it the number of weights, right? Real numbers? Or is it the number of bits? Right? Because packed learning needs that the number of machines is 2 to the m. So it's depending on it being bits, right? But in practice, we have real numbers, right? So you can also ask, what's the difference between this? And of course, we like x's to be 0, 1. But in practice, they're real numbers, right? So if you're asking, what does packed learning do for us? In this scenario, it does nothing because we don't have that the number of machines is bounded. The number of machines is infinite. And the number of inputs is not 2 to the n. It's right. We want the number of inputs to be 2 to the n, but it's also infinite. And so all the packed learning papers I read were, how do you get the number of training data, the amount of training data you need to be not infinite, but 2 to the n, right? Which isn't what we want. 2 to the n is, right? If you assume it's bits, then it's a log of that, right? So, and what I've heard is that in practice, there's no difference between what does this real number contribute? Well, in some ways, it's kind of more like a bit than it is like a real number, right? Yes, we're all agreeing in terms of packed learning experience, right? I'm just saying, in my 1 month of looking at this, I haven't found anything.
So the gap to packed learning is that packed learning has to work in every distribution, and maybe the distributions which are being looked at are not every.
Yeah. If you take a random wise, then packed learning doesn't work. Right? Packed learning says, if you can find a machine that solves this problem, it will if you can find a small machine, if you can find a machine from amongst a very small set of machines that solves the problem, then it'll generalize well, right? But if the outputs are random, sorry, you're not going to find a machine in the small set of machines that generalizes well, right? VC dimension kind of, if you need to be able to look at all of the functions. If you want to be able to find all of the functions, your machine needs to be able to compute all of the functions, right? So you need high VC dimension, which says that you're basically, right?
So there are no interesting simple class of functions that one can then prove that generalizes well for this class?
Well, it all comes back to what these guys have been doing since we were born, you know? What can you say about functions that we use in everyday practice? Can we say they need small circuits? Can we say anything about them, right? And we can't.
Again, in the pack learning, they do something.
What they do is they bring it from infinity back down to exponential.
Yeah.
They don't bring it down to polynomial. It's my understanding.
Well, I haven't thought about, haven't ever worked on pack learning, but what I recall from it is that they have, for some restricted types of things, you know, most of the results are negative, but there are a few small classes of things that you can learn with, you know, in the sense of, you know, this
Right.
concept class or something like that, and you learn it.
Right.
So,
Right.
back to this discussion, I mean, you'd like to think that there's something we could say positive about some very restricted kinds of things.
Right.
I mean, probably not very interesting to the people in practice because
Yeah.
they're much more ambitious.
Right.
But in terms of a theoretical result, is there anything to be said about what can be learned
Well,
from neural nets?
if I didn't learn this last month, I had to go back to when I was a graduate student, and then I remembered them saying really simple things like, you know, if it can be done by depth
DNF
2,
or something, yeah.
right?
Yeah.
Then, right, but that's not what we're talking here, right? We're trying to recognize cats and dogs.
Yeah, yeah. It's bigger. Surface. So the bottom line of all this, I guess, the people, if I were a machine learning neural nets person who really is interested in results and everything, this whole exposition is okay, yes, and ho hum, but it's not, doesn't influence my life. Is that what the bottom line is for the ML people? Or not? I mean, I don't. I mean, I still think it's a surprising result. Don't get me wrong.
Yeah.
But would even if somebody who's open-minded and says, yeah, that's surprising, but they would walk away from it and says, but now I don't know where to go from here.
Yeah, I think that's the bottom line. I think I mean, if you just are a naive coder and you throw data at things and you do set your weights in weird ways and it doesn't work for you, then reading this paper will say, well, we really need to set our weights in very proper ways. But I think the practical people already know how to do that, right? They're already doing this. They already know that you want your weights to be normal around 0 and very small.
The initial weights?
Initial weights, right? And then exactly what do you set it? Well, you don't want things to blow up. And I assume practical people already know you don't want it to blow up, right? And here you want these derivatives to be small. Well, practical people already know you want the derivatives to be small. So I would say, if anything, this paper was guided by what the practical people figured out more than the other way around.
Oh, for sure, because they've been doing this without any theory.
Yeah.
So we know that.
Yeah.
That they weren't influenced by theory.
Yeah.
But it's, I don't care about that. It'd be nice if theory could explain something.
Exactly. Exactly. And yeah, I mean, I thought it was just that it's working at all was complete magic. And the fact that this says that you're going to, at least in this one weird case, you can prove you can find the optimal in fast time. I think that's worth knowing, right?
It's not one, you said one weird case. No, you're going to do it in.
Oh, I meant
generally.
the one weird case where we're over-parameterizing that's not, you know, the only, yeah, if you over-parameterize it,
If
it
you
works.
over-parameterize, it's unbelievably general.
Yeah.
Some sense too general. Yeah, it's interesting. But you say, do the ML people know this result?
No, I'm surprised how I have not had people say I know it. guy in Vietnam handed it to me, and otherwise, I don't know it. The people I've talked to didn't know it. In fact, somebody who came to my talk, who's a machine learning person, said he's written papers of very similar natures, which just reading his abstract, I don't believe, because it contradicts this. And he didn't know this.
We should ask the people here, like Roger Gross and David Duvenel and those people.
Right.
I mean, I'd be surprised that they don't know it, but possible.
Yeah, maybe they, yeah.
There's one other person. Scarborough, get his, who am I thinking of? Yeah, Roy, yeah.
Well, certainly if you look at the citations, it's been cited lots.
This paper's been cited lots by ML people.
I didn't look, it just, Google tells you how many citations.
I know that, but yeah, it'd be interesting. Okay.
Okay, great. Any other questions? Okay, great. Thanks a lot.
The slides are on my webpage if you want to finish them off.
Nice to contact a couple of people in this, I think, of our current ML. I want to say young.
Yeah.
Yes.
Faculty.
So you're teaching. Yeah, that's it.
Hello. I have some new ideas of like the 7 case.